Welcome back. This is Peter Dubin going over the second session of this idea of barometric pressure being used to measure the density of air. And I have another purpose for this video, and it is to show people, especially math students in high school, that exponential functions can be useful. They're not just mathematical abstractions. So basically, in our last video, we demonstrated or derived this formula for the pressure at any particular altitude h. It is P is equal to P sub 0, that is pressure, the barometric pressure when h is equal to 0, times e to the minus rho sub 0 over P sub 0 times g times h. And if we organize these terms and take the natural log of each side, we can solve for rho sub 0, which was equal to minus P sub 0, ground pressure, divided by g, gravitational acceleration, times h, times the log of P over P sub 0. And we can get values for all of these things, and we can actually generate a number. What I found in doing a search one day was that exactly the right circumstances turn up in terms of the Eiffel Tower. When the Eiffel Tower was opened up, I'm not sure when its opening day was, but scientists put a weather station on the base, or close to the base, and then one close to the top of the tower. There was a distance between the two of 279.5 meters, and they actually recorded the barometric pressures at the base and at the top for different months. And for the month of January 1889, the average base pressure, P sub 0 in our case, was 760.65 millimeters of mercury. And at the top, the average pressure for that month was 734.61. So that is exactly what we were looking for in order to actually derive the density. We want to use this formula. We're going to put P sub 0, that's 760.65. I'm going to have to change the units here. This is millimeters of mercury. I have to actually change that into like newtons per square meter. So that's what I will do, I think. That's what I do, yeah. And in order to do that, I'm going to let you look down here a little bit. What I've done here is I've tried to calculate the pressure for a meter cube first of water, and that's just simply 10 to the 3 kilograms is a meter cubed of water. Then what I'm going to do is multiply that by the weight of mercury. In other words, if the cube was filled with mercury, it would be exactly 13.6 times that amount. And then we have to remember that the column of mercury was not really a meter, but it was 0.76065 meters. And if we multiply, this will give us the mass in a kind of, it won't be a cube anymore. It'll be a little bit short of a cube, but what we're going to do is we're going to multiply this by g, gravitational acceleration, and we'll get actually the weight of that mass of mercury. And if we divide then by a meter squared, which really doesn't change our numbers, we end up with this pressure, 101,379 pascals. Pascal is the unit of pressure. Now, but we don't want this P sub 0. We want rho sub 0, which is the density. So what I'm going to do here is I put my numbers in here, my 10 to the third kilogram, 13.6 times that gives us the kind of mass of mercury. But it's going to be short of that since our column was not really 1 meter, but it was 0.76065 meters. I'm going to erase that, sorry. And then if I multiplied that by G, I would get the weight of that mass. And then if I divided by a meter squared, I would get the pressure. But what I'm going to do instead is the G up here cancels with the G here. I have a G here, a G here, so I don't need to mess with G actually. I just divide by the height, and then I'm going to generate a number here, which comes out to about 1.289 kilograms per meter squared. Sorry, that's per meter squared. It's per meter cubed, which is the density. And this has to be meters cubed too. The point being this, that the standard measure of that by the powers that be are about 1.2754 kilograms per meter cubed. But that is at 100 kilopascals, and we are actually measuring it at 101,379 kilopascals. So as it turns out, if we were to make the correction, we would end up getting 1.2715 kilograms per meter cubed. It compares, for whatever it's worth, somewhat favorably with the standard number for that measurement. So this is part 2 of my presentation. Part 3 will be seeing if we can find out what the air pressure is at the top of Mount Everest using these numbers, because now that we have rho sub 0, we can put it in and we can put different numbers in for H and see what the air pressure is. So thank you for listening.